Okay, let's continue number 11. So this was our recurrence relation that we obtained. So now let's go ahead and explore this relation and see what we obtained from our CNs, for CNs. Okay, so if n is equal to 0, then, okay, 0 plus 2, so I get C2 equals C0 over 0 plus 2, 2, 0 plus 1, 1. So I'm going to leave this as 0, C naught over 2. If n is 1, C1 plus 2, so 3 equals C1 over 1 plus 2 and 1 plus 1, which is 2. And notice I'm actually going to leave it as 3 times 2, which we know is 6, but there's a reason why I'm leaving the factors as they are. Okay, so if n is 2, we get C4 is equal to, C is 2, so C 2, 2 plus 2, 4, 2 plus 1 is 3, and erase this part. And actually, I just want to, before I forget, okay, so here we have C naught over 2, and here I had C1 over 3 times 2, and usually we replace C1, right, in terms of C naught, but notice there isn't a C1 yet, so we leave it as it is. But here we have, this is equal to, we actually have a C2. Our C2, right, is right here. And so I really have, okay, times C naught over 2. And I'm going to leave this as C naught over 4 times 3 times 2. Again, which we know is 24. But again, there's a reason why I'm leaving the factors as they are. N equals 3. Okay, so it's just, again, substitution. So we have C, n is 3, so 3 plus 2 is 5. So we have n is 3, so C3, 3 plus 2, 3 plus 1 is 4. And we have a C3, right? It's right here. So we can replace this. So C3 is C1 over 3 times 2, again, which was our 6. And this is really C1 over 5 times 4 times 3 times 2. And hopefully you start seeing why I'm leaving these factors as they are. And finally, oh, let's do one more, or maybe two more. Okay, so 4, C6, actually this will be the last one. C6n is 4, so we have C4 over 4 plus 2, so that's 6, 4 plus 1, which is 5, and equals, I made that division bar too long, equals 1/6 times a fifth times C4. Do we have a C4? We do. It's right here. So C0 over 4 times 3 times 2. And again, that's C0 over 6 times 5 times 4 times 3 times 2. Okay, so let's go ahead and write this, our CNs, nicely without all this intermediate work. Okay, so we have C1, or C2, is equal to, okay, C naught over 2. C3 is equal to C1 over 3 times 2. C4 is equal to C2. C4 is not C2. C4 is C naught over 4 times 3 times 2, C5 is C1 over 5 times 4 times 3 times 2, and C6 is C0 over 6 times 5 times 4 times 3 times 2. So again, hopefully you can see the pattern. This guy, I mean, this is really C0 over 2 factorial. This is C1 over 3 factorial, right, which is 6. C0 over 4 factorial, which is our 24. C1, which is 5 factorial, right, or 20, or 120. And then C6 is C0 over 6 factorial. And sometimes, I mean, it's easier not to multiply it out if you're having trouble seeing the pattern. I think the book multiplies some of them out, but you don't have to. So here, notice that, so all the problems so far, after we found our recurrence relation, we found our Cn, and it was in terms of C0, but here, right, C2 is written in terms of C0. Okay, C3 is of C1, C4 is of C0. So we have, let's see, maybe, right, this guy, right, these, right, C2, C4, and C6, which notice the subscripts are even, are written in terms of C0, and our odds, right, C3, C5, right, if you wanted to write a C7, these guys are written in terms of C1. So there's your C1, C1, and that's basically it. And might as well box these guys. Hopefully that makes sense. Okay, so our goal was to find, again, a power series solution, of course, if it exists. And see, we called it, right, Cn x to the n. And we have C0 plus C1x plus C2x squared plus C3x to the third plus C4x to the fourth. And I'm writing more terms just because we have more terms in this case. C5x to the sixth, that's a C5x to the, let's see, 1, 2, 3, 4, that's a 5. Plus, okay, let's just write dot, dot, dot. So now let's input our values, our C1s or C0s. Make this a little bit bigger. Okay, so C0 is just C0. C1 is just C1x. What is C2? Well, C2, we have C2. We actually have C4, and then of course we have a C6. So C2 is C0 over 2 factorial x squared plus C3. Okay, our C3 is C3 is C1 over 3 factorial x to the third. Okay, so maybe, right, this is the blue, this is the purple, plus, okay, so I did this one, and now I'm doing C4. C4 is blue again, so that's C0 over 4 factorial x to the fourth, and again, that's my blue part. And we can move on to plus C5, and C5 was purple. All right, there's our C5, and might as well make this purple. C5 was C1 over 5 factorial, and all of this is x to the fifth. And then we had the last term, so might as well write in the last term. Plus, right, and then our last term, C6, right, was C0 over 6 factorial. all x to the 6th plus dot dot dot. Okay, so notice we have this blue purple pattern. So we're gonna write a familiar, right, elementary function in terms of C naught and C1. Okay, so we have, I'm going to go ahead and rearrange actually the purples and the blues. You don't have to, but it's, I think it makes it easier to see this. So let's do, okay, C0, my C0. So C0 plus C0 over 2 factorial x squared plus C0 over 4 factorial x to the 4th plus C0 over 6 factorial x to the 4th plus dot dot dot. Okay, that is, right, these are my blue guys. And now let's just write the purple. So we have plus, let's see, C1x plus C1 over 3 factorial x cubed plus, where am I at? C1 over 5 factorial x to the 5th plus, okay, dot dot dot. Right, these are my purple guys. Okay, so we, again, the very, maybe, I think in problem 2 or 6, after we input our, C naught, we usually factored our C naught. But here we actually have C naught and C1, so we're going to factor both from each infinite sum. So I'm going to factor out a C naught here because we can. 1 plus, and I can write this as x squared over 2 factorial plus, or you can write 1/2 and then times x squared, which is the same thing. X to the 4th over 4 factorial plus x to the, and that should be a 6. X to the 6th over 6 factorial plus dot 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 plus, similarly with C1, we have x plus x cubed over 3 factorial plus x to the 5th over 5 factorial plus dot dot dot. Okay, so we've done the hard part and a very tedious part. But remember the problem, right? The goal says to find 2 linearly independent power series solutions, right, of this given differential equation. So here are our, here we have power series, right? Infinite power series. Here's an infinite power series. So does this remind you of any power series, any of the familiar transcendental power series on page 195? And does this remind you of anything? And if you actually look on page 195, the blue is actually hyperbolic cosine of x, and the purple is actually hyperbolic sine of x, right, or sinh of x. And these are our linearly independent power series solutions, right? We can write that again in terms of these coefficients, C naught and C1, which are arbitrary. So that is our final answer. This, right, this is really y of x equals, right, that's the solution to the differential equation above. And I think I will find the radius of convergence in the next video.